Here is our second conversation for Chapter 12, and we're going to get into some civil engineering. We're going to look at tension and compression, and we're going to look at arches. This is some kind of fun stuff. Imagine that this beam, this is called a cantilever beam, and imagine that it's actually a stack of springs. The spring on the very top, when there's a significant load put on it, like a person standing at the end of the diving board, a spring on the very top is going to have the atoms pulled apart. So what's happening on the top layer is a pulling. We call that pulling tension. What's happening on the bottom is a pushing, and we call that compression. So the girder that is shown, which might be a big old hunk of steel, has tension on the upper side and compression on the lower. This little line in the middle is calculated, and they call that the neutral line. So that would be the layer of atoms that are neither being pushed nor pulled. But everybody else is being pushed and pulled, and the further away you are from the neutral line, the greater the degree of push or pull is that you have. The last picture was cantilever beam. This is a suspended beam, and same thing with our massive load coming here. It is causing the atoms on this side to be pulled apart, and the atoms on the upper side to be pushed together, and it has to do with the arc of the bend. Like our last example, we do have a neutral line, and if you were to do a vector diagram on this, you have got supporting forces and you've got your load. Okay. When we've looked at these before, we have assumed that the item is rigid and doesn't bend, but in fact, in real life, they do. One of the ways that we counteract this is construction materials use an I-beam, which would be a section of steel or an assembled wooden member nailed together in the shape of an I. And we're going to call this is the flange, and this is the web. And in industrial and construction situations, there's all sorts of different proportions of I-beams, as well as recipes for the steel that they make them out of. This is particularly strong because the bulk of the material in the I-beam is going to be located in the area that's under tension and under compression. That's think of a whole lot of springs stacked up together. And this is an efficient thing to use because the web in the middle encounters the least amount of stress, so we can remove weight from our construction and not lose strength. Right, here's a question for you. Suppose that you are drilling holes through the tree branch, and you have a choice of 3 different places to put the hole. Where will it weaken the branch the least? Think about our little man here wanting to later on put a load on the branch, and maybe he wants to hang from it or stand on top of it and jump on it. Which hole is going to have the least impact on the strength of the branch at a later point? Well, the middle of the branch is the neutral layer. So when there's a load on the end of the branch, it will the surfaces will be under tension and compression, and there will be less or no stress in the middle. So it would not weaken the branch to remove material from there. Arches are special consideration of how we take advantage of this compression and tension. How do we build things? And you can actually date an ancient structure based on the construction methods that are used. The very oldest, and this is an example from the Greeks, um, the people had not understood yet the advantage of arches and how they can be used. And so to support the roof on the top of the Pantheon, um, the Parthenon rather, um, so this massive roof needed many, many, many massive columns to hold it up. What the Romans did, the Romans were fabulous engineers. What they did was realized that the geometric structure of an arch has significant advantages um, for because every member of it is in compression. You've got a video that describes this more carefully. Stone is the best material for withstanding compression, and a beautifully built arch can last much longer than the civilizations that built it. Another extension of the arch is a catenary, and that's the idea where an arch supports only its own weight, which is beautifully shown here with the design of the gateway to the west, also known as the St. Louis Arch. Beautiful piece of engineering, and in the case with the student here, he is holding a chain that is only being pulled by its own weight, and it makes the same arch. This is also the shape of an egg and other shapes that you will see in nature, and should look like the parabola when we looked at projectiles and throwing a ball. So it's a very common shape found in nature. Um, a cool thing about a two-dimensional arch is that if you rotate it, so imagine that this kid was spinning right where he's at, that arch will turn into the shape of a dome. And this is kind of dome building in Renaissance Europe was kind of the rocket launch at the time. And the big, beautiful cathedrals, the Vatican, other cathedrals, the idea that you could build a dome on the inside takes away so many supporting columns and is a good combination of engineering and architecture. You've got a video that goes into some conversation about how that distributes the forces. You won't need to do problems like that, but it's important for you to kind of see that discussion, why that works for us so well.